Intel's next-gen processor, Panther Lake, it's built on core technologies that have evolved throughout the last couple of generations. We have seen it go from Alder Lake all the way to Meteor Lake. I am Alejandro Hoyos, and in this episode of Talking Tech, we're going to take a closer look at the microarchitecture, which is a hybrid architecture, and how we have two types of cores. We have a performance cores and efficient core. Join me in the road to Panther Lake.
The reason I'm especially excited about hybrid architecture with Panther Lake is in Lunar Lake, we proved the architecture in a very exquisite mobile phone-like fashion. With Panther Lake now, we take a very friendly PC ecosystem approach, and so the OEMs are able to adopt these products in the way they like to design PCs using their tech.
Okay, so let's start with hybrid compute. What is hybrid compute?
Okay, so let's kind of take a step back and talk about execution on SoC in general, right? Mm-hmm. Hybrid compute basically means that you have different capability IPs on a system that are able to handle different things. And you put it on same SoC and bring it to market. Now it could be CPU execution, it could be GPU, NPU, anything that we put in there. In our case, for example, what we did with our hybrid solution starting Alder Lake was we combined two different microarchitectures on the CPU side on a same SoC, and we kind of had a performance hybrid architecture. So we had P-core performance hybrid architecture and E-core, and we combined them on the same SoC, and that's how our hybrid compute came to effect.
Hybrid compute architecture is where you can control where to run your task. The idea is to build a curve that you can show when you run a low demanding performance task on the E-core, which is much more power efficient than the P-core. But when you need high performance, you run it on the P-core. The system today and the operation system know today to identify this low demanding task and high performance task and allocate them to the E-core or to the P-core. In addition to that, mainly on the computer, but in addition to that, we are using the Iceland, which is working on the E-core. And what we are trying to do is to run all the KPIs of the battery life, like Netflix or YouTube or Teams. We are trying to allocate them only to the Iceland, to the E-core, which is separated. And by that, we can shut the P-core and E-core that on the CPU die and save all the power. So the idea when you run battery life is to save the power of the CPU tile and run it only on the Iceland. So this is another usage how we use the E-core and gain much more power efficiency than in the past.
A few years ago, Intel decided to head down the path of different cores within the same system. So we have what we call E-cores, the efficient cores, and we have P-cores, the performance cores. The first mainstream product for it was Alder Lake, where we had a mix of Golden Coves and a mix of Grace Monts that we put together in the same package, those E and P cores. We did that so that we could bring performance and throughput to the customer at an effective cost. So, the E cores are a little bit smaller than the P cores, but they get to work together. They run the same ISA, they run the same software, and you get more cores in your system, and you get more throughput with those additional cores in the system. So that's where we started.
When we introduced the low power island for the first time was on Meteor Lake. It was running on lower frequency, and the amount of cores was even lower. We didn't allocate many cores for this battery life task. We learned from this that we can be more efficient because once your KPI, for example, if you run Teams and you're adding video, for example, then you need to run more. We need to get more performance. Then it was, of course, activating the P-core and the ring and the fabric and consuming more power. So what we did on Lunar Lake is that we increased the performance of the E-core that may be able to sustain all these KPIs in double the frequency, double the number of cores, but we still have an Iceland. And today what we see is that most of the KPIs that we are running on this E-core, and they don't need all the other cores. And this is what brought us to much more power efficient product. And this is, by the way, what we are doing also in Panther Lake, and we are leveraging this goodness to the other product.
Why did we took this route to go to the hybrid compute? Why have two types of cores?
Yeah, that's a great question. So our intention, and we were first to market, I think this is one of the inflection point we had in Intel's journey, right? Performance hybrid architecture is something really Intel brought to the market. If you look at it from a perspective of what hybrid compute has been done in the past, it was mainly for efficiency and others' perspective. What we really did in Alder Lake was, we basically said that, okay, if we take E-cores, right, the area and all the trade-off that we have, we are able to fit 4 E-cores in place of 1 P-core that we had with SMT at that time. And you can see that in desktop, when such usages, multi-threading is increasing, right?
Right.
So the more performance we can offer to our end users, it's better.
Within Intel, we started developing different cores for different use cases. So we started developing a low power core line in addition to our performance core line to try to go after, sort of smaller form factors, phones, tablets, low cost laptops, low cost computers. Mm-hmm. So internally, we had naturally developed 2 core lines. The change was when we started to put those into the same system. Originally it was Lakefield, then it became Alder Lake, then Raptor Lake, then Meteor Lake, then Alder Lake and Lunar Lake, and so forth. So because we had the 2 independent developed databases, the 2 different IPs, that's what gave us the ability to put them together into a hybrid system.
If you can recall, where did the hybrid compute journey begin?
Yeah, great question. So I don't know how many people remember, but we first had a hybrid architecture with Lakefield. Mm-hmm. This was way back when, and the intent there was, we had 1 P-core there that time. We didn't have a P-core E-core terminology that time, but right. We had equivalent of 1 P-core and 4 E-cores, right? The intent there was different. It was basically to maximize efficiency for a certain SKUs or thermal power budget that we were shipping, right? It was a very small segment.
Right.
But we learned immensely from that. We learned that what is needed to enable software stack when you combine 2 different microarchitectures, right? What is needed, what kind of hardware guidance might be needed when we want to scale this further? What software enablement, ecosystem enablement is needed to get software readied for such kind of approach that we have. So we started it in Lakefield, even though it wasn't like a big scale product, it was right. Very niche for a certain market. We learned a lot from that.
No, that is great. So Lakefield sounded like it was a little bit of a proof of concept to see how it goes. And you said like for a niche market, but then we move on to the next thing, mm-hmm. Which I think it was Alder Lake, which was the first big hybrid compute architecture.
Absolutely. Yeah. Alder Lake was where we kind of said that, hey, we want to, use P and E cores to maximize our performance. Now we put E cores on the same ring on Alder Lake, the faster ring that we have,
right.
Because our intent was performance hybrid, mm-hmm. right? So we started with that. We had that 4 E cores to 1 P core trade-off. We got maximum performance benefits out of it. Our launch configuration that time was 8 P cores and 8 E cores, which yep. turned out quite well. And then we had, hardware assist and thread director and other technologies helping us out to guide the scheduling decisions and work with our software vendors such as Microsoft was huge, right? Because then we could bring the product to the market, show all the performance benefits that we get.
What were the challenges like for the ring bus and all the different configurations for that?
Yeah, absolutely. So when we talked at ITT, we were focused on Lunar Lake and mm-hmm. not as much Arrow Lake at the time. So there we talked about how we took that low power island, there was no ring, there's no LLC, there was a system cache that we could use, and it was closer to the memory channel. So that is one context in which that module, that E-core, could work. And so when that's active, when that's running, you have a lot less things alive, so that right. That's the good battery life. Now with Arrow Lake, we took that exact same design and we placed it adjacent to the P-cores on that LLC, that ring fabric, right? And so now you take something and you add a nice performance feature, a big cache, right? And so the performance gets better. The power scales quite nicely. And so, it's just 2 completely different contexts for that same core. And that's the type of thing we're bringing to Panther Lake.
There is challenges, of course, that we need to make sure that the ISA is aligned between the cores, but this is an architecture thing. 2 different cores have different requirements. Usually, the E-core is more power efficient and need to run tasks that, again, less demanding from performance perspective, but more efficient from power perspective. So even when you run as an SoC, as a design team, you need to target these frequencies and the PV curve of the E-core differently than the P-core, because you need to treat them differently. Also, there are two cores, two different cores, sometimes two different interfaces, different power management scheme. So once and by the way, controlling the power management of these cores is the heart of the power efficiency and our ability to control power management, which rely on many heuristics in the system. E-core and P-core sometimes behave differently. One of the, again, challenges is there are challenges between the two cores, but as we move forward, we see more similarity between the cores, at least from design perspective, but still, these are targeted to two different purposes, and we need to handle that during the design stage.
How complex was it? Because you have two types of cores, and then you have, like at the high level, you have a shared cache. Did that create any complexities, or was it just, business as usual, or something you have to come up with like a creative solution?
Yeah, if you look at the E-core line, kind of what had happened was it started as a single core with threads, and then it became two cores that shared an L2. And then by the time you got to the Gemini Lake transition, it was four cores that shared an L2. And we've continued with that building block throughout. So this is many generations through on that shared L2.
Right.
Going into a system that didn't have an LLC, that was a bit new for the last few generations. And so that brought a different set of challenges. Power management, we have per core power domains, C states so that we get good battery life. All that goes within that module, so that adds a little bit to the complexity. But it's something we've built a number of times before. And then optimizing the system when you don't have that ring, when you don't have that big cache. There's another set of pieces that we had to do for that generation and the new generation.
You said the low power island. Can you, for the people who are also new, can you expand a little bit more what it is and how is it different from like the efficient cores and the P cores?
Yeah, so if you have cores on a high-speed fabric, and that high-speed fabric talks to the rest of the system, then kind of your cost to do everything goes up a little bit, right? So if I'm running, say, Microsoft Teams,
right,
and I need a couple of cores, I want to keep it smooth, you want your video to play, you want your audio to play, subtitles, etc., right? That's the kind of workload we want to get on that low-power island. So it's sort of the minimum that you have to turn on to be functional. So with the low power island, we don't have to turn on the ring, we don't have to turn on the P cores, we have a shorter fabric to memory. And so that gives you the ability to have functionality and performance without some of that extra power cost. And then that leads to that improved battery life. So we could put it on the ring, it's just going to be slightly more power to accomplish that. So that's kind of the trade-off.
So when Alder Lake came out, this was the first time we actually heard about the performance cores and the efficient cores. And just because, I guess, of the name efficient cores, it gave the perception to the people that they were not going to be as powerful or perform as much as the performance cores. But that's not the case, right?
Yeah, so we've actively tried to improve the performance of the efficient cores while maintaining efficiency. So if you look at the E cores that we had originally in Alder Lake, and then you go to the ones in Meteor Lake, you get some performance uplift. When you get to Arrow Lake and Lunar Lake, you see even more improvement in that performance. And then we continue that into Panther Lake, and so the goal here is to improve the E-core performance while maintaining efficiency for battery life, for throughput, for TDP-constrained scenarios. And we're doing that with a goal of having more and more workloads feel comfortable running on the E-cores, especially when we can get it onto that low power island. So these are not slow cores, they're not boring cores, right? They're actually incredibly powerful these days, in spite of the fact that we call them efficient cores.
Right, because I think I remember your presentation from last year saying like, okay, this SkyMount cores perform better or as well as the, I think it was the Raptor cores or the...
Yeah, so I had a chart that was basically if you put a SkyMount on a ring, then this would be the relative performance.
Exactly.
And there we said this would perform similarly to Raptor Cove on a certain set of workloads. If you had an Alder Lake and you were happy with that P-core performance, you're now getting that out of an E-core. Now, we don't push it to as high a frequency as you do in Alder Lake for desktop and gaming, et cetera, but it still runs at a, in Arrow Lake, for example, we would run the E-cores over 4.5 gigahertz. So it's still a pretty healthy frequency.
Yeah. When we are talking about the evolution of the cores, can you tell us a bit more of how they have changed, let's say, from one to the other, and how they have improved?
Yeah, absolutely. So, there's multiple pieces to any CPU microarchitecture. And, one of the ones where we pushed hard is, say, branch prediction, right? In our P-core, we tend to run ahead on terms of capacity and history and accuracy, and we will continue to evolve that over time, absolutely. We think there's plenty of room left to do evolutions there. So that's one aspect we do pretty heavily in our CPUs. That's true for both E and P. Cache size, right? Everybody wants more cache, and as a CPU architect, I love more cache. It's my favorite thing, right? It's just a little expensive sometimes. And so, bringing more cache to the product, right? That's the type of things we're doing at the SoC level as we evolve. Our cores are tending to get a little bit wider and deeper over the generations. The more you can do, the better your branch prediction is, the more speculation you can handle, the deeper and wider it is. You get value out of that. So we continue to evolve on that aspect. And supporting more bandwidth and being able to miss more and go and fetch more data because in the days of modern computing, things are very hungry when it comes to memory bandwidth and cache capacity. So we need to make sure we build the things into our cores that allow us to consume that bandwidth. So more queuing, more prefetching, more accuracy of prefetching, right? These are things we're bringing to both core types because we want to solve today's computing problems.
Yeah, that's great. I also see that there has been like a little bit of evolution of the decoder. Like I think it was first it was 3 decoding 3, and then it was like 9 instructions at the end. Well, not at the end, but with the latest one.
Yeah. So we absolutely are starting to widen our ability to decode in the front end, right? So that gets us to understand where the instructions are, that gets us to predict branches faster. On the E-core line in SkyMount, we introduced a peak of 9 wide decode built on 3 decode clusters. On the DSP side, on the P-core, we continue to widen what that's capable of doing. We're 8 wide ALEC and the DSP can deliver that. Our Might is able to deliver more for that as well. Again, a lot of this is about making as much software faster as we can. So some of these things will not apply to all software, but the pieces that it gets benefit from, some of your more complicated database workloads, things like that, that's where widening the ability to decode and getting to misses faster, et cetera, really pays dividends.
Throughout the whole evolution of all the cores, you guys have done a lot of changes when it comes to the front end and back end, and also new and revolutionary things, I guess to say. Can you touch a little bit on those?
Right. So, the front end that we've built in the E-core is a little bit different than the front end in the P-core. So there's just different trade-offs there. On the P-core side, we have a DSP that we call it, right? A UOP cache, something that holds decoded instructions. On the E-core, we've taken a slightly different approach. Instead of having to pay for that cache, instead we have what we call clustered decode in the front end. So it's just another way of solving the x86 decode challenge, which we believe we've solved. It's variable length, so different microarchitectures. So that's one of the benefits that Intel's been able to get by having multiple CPU teams working on multiple microarchitectures. We can get innovations from both core streams, and we have things that we find on the E-core side that we implement on the P-core side, and vice versa. We absolutely share and go back and forth. So, while it's maybe a little bit more effort to produce the 2 CPU streams, we've gotten some really, really nice benefit out of that.
Oh, that's great. So P-cores and E-cores are being developed in parallel, and any advancements each team gets, you can actually share.
Absolutely. So we're a team that works together to deliver it now. We've changed that a little bit. We're working more closely than we did in the past so that we can deliver a broad portfolio for Intel and make sure our P cores can be as efficient as they can be and our E cores can be as performant as they can be, and we can deliver a total system solution.
What has been kind of the most challenging thing that you have run into throughout the whole development of the E cores and P cores, or the whole architecture as a hybrid architecture?
So hybrid has gone reasonably well from a hardware perspective, right? We have protocols, we have ISA, we have firm contracts. Over the years, we've gotten better at our software interfaces for scheduling. So everybody's got different workloads, everybody wants battery life here, performance there, you've got games, you've got all these things. You know, Intel has introduced and provided Thread Director to the ecosystem, right? And so that's our way to help ensure that tasks are scheduled effectively, right? We want to make sure that tasks that games don't care about aren't running on the P cores when you're playing games. We want to try to get Microsoft Teams onto the CPUs. So the software side has been something we've been able to evolve gen over gen. And by the time we get to Panther Lake, we've actually made some really nice optimizations that should help that user experience and battery life and performance all together, because when you schedule in an ideal fashion, you use the hardware to its best advantage. And so that's been one of the places where we've done a lot of really great work that probably, you know, we didn't guess how much work would be required there, but, you know, we've been able to make some really nice improvement.
For the people who are seeing us for the first time, I want to do a little bit of background on what is Thread Director.
Okay, so think about it this way. If we have two different microarchitectures, we had same capabilities. So for example, from instruction set perspective, both P and E core execute same instructions.
Right.
There is no difference. There is nothing going to be one is going to faulting because I don't support this instruction. No, we do. They are symmetric instructions across them. But just because they are different microarchitectures, such as internal resources are different, cache sizes, capabilities, etc. are different, you are going to have different performance on them. Right? We measure it in terms of IPC, instructions per cycle. And so you take a certain instruction like VNNI, if you have more resources on P core, it's going to be faster. On if you have relatively lesser resources on E core, it's going to be slightly slower. But we want to be able to point or guide operating system that, hey, on this specific microarchitecture, right, these are the IPC differences for certain instruction sets. So we recommend put these threads on these cores. We don't own scheduling. Microsoft owns scheduling, right? Operating system owns scheduling. So we provide a hint or recommendation. And to provide that hint or recommendation, the infrastructure that we created, it's the Thread Director. So it has two pieces to it. One is that sits in the core, which does the classification of instructions, right? Yeah, which basically says that, hey, we have 4 classes, class 0, 1, 2, 3, and it puts it into different buckets saying that, which class do I belong to, right? The core does that at a nanosecond level because it's running very fast.
Right.
But then there's another piece that sits in SOC, which has a table, and that says that for every class, what's the most performant core and what's the most efficient core. And then using that, we kind of guide OS saying that, oh, are you seeing class 2 instructions? Here, your most performant cores is this P core, or your most efficient core could be also another P core, right?
Right.
So we provide that hint to them. That's how the whole Thread Director came about.
Okay, so that makes a lot of sense. So what is Thread Director kind of gives a suggestion or a recommendation to the OS, depending on the table that we have, of where the workload should land, on which core it should land. How did Thread Director came about? Because this wasn't just like one day you said like, oh yes, we're going to do Thread Director, I think it's great, right? There was probably some thought process that came.
Absolutely, yeah. So when hybrid decision was made, we had at that time, the P core and E core used to go its own SOCs, different products at that time, right? Now we are combining. So one question that immediately came, and I'll pick an example of VNNI. This is the AI, CPU-based AI instruction that is gaining popularity quite a bit on Int8 operations and things. And when we kind of decided that Alder Lake is going to have, P and E cores combined, we knew that there is a performance delta on how VNNI is executed on P core versus E core.
Right.
Now think about a scenario. Okay, I have 2 threads running from operating systems perspective. They're ready to run. Okay, and I have 1 P core available and 1 E core available. One thread is doing heavy VNNI. okay, which means class 2 if you look at our current class definition. And the second thread is doing like scalar integer operations or scalar floating point operations or something, which is class 0 because the IPC or relative performance is similar between P and E cores.
Okay.
Operating system had no way of knowing that, oh, on this particular Alder Lake, VNNI has this much delta, because then you're overloading operating system if it tried to build everything in operating system at that point, but it had no way of knowing that, right? So we needed an interface to suggest to operating system that, hey, if you are running this type of classification, because our core is telling you what the instructions are, then use these recommendations from hardware to guide the thread to a most performant core. And so in order to solve problems like this, or if you had another example of, one thread is spinning, waiting for work to show up, and another thread is doing real work, we want to send real work to the most performant core, right? So how do we guide operating system with that? And that's how the thread director overall design came about, right? So first step in there was working with microarchitecture like Steven and P-core architecture, etc., to kind of get together and figure out the IPC deltas, create right telemetry infrastructure. And then the next step was working with our SOC architects to kind of build the whole thread director infrastructure and table. And the third and the most important step was working with our OSVs. Partners, right? Be it Microsoft, Linux, Chrome, etc., to see that, hey, we are providing this. Is this what you expect? How would you use this hint, right? Help us make the right design on interfaces, communication mechanisms, protocols, so that we send you the information that is relevant for you guys. So that's how it kind of came about.
No, that's great. And actually, kind of that leads in the question that I wanted to ask you earlier, which is, how do you enable this whole ecosystem? Like, who do you have to work with to bring thread director alive, right? It's not only within Intel, right? There's other things that we need to, other partners that we need to work with.
I mean, internally, we had all the kind of brain power behind it to, create telemetry, classification, core side of things, SOC side of things, P-code tables, etc. There was a lot of collective effort across organizations, Oregon, Israel, Santa Clara, all these different sites working together. But at the same time, we also had to work with, and one of our key partners on desktop, client side is Microsoft, right? So we had to work with them kind of, we had a very productive collaboration, and it's still ongoing because we have more and more products coming out, is, okay, if we send this information using these interfaces, how would you kind of initialize it, use the information? They had certain requests that, hey, don't send us too many updates, because I understand from their perspective, they have to process an interrupt, react on it, right, based on their decision. And they ultimately they own the scheduling. We provide the hint. So we wanted to make sure that we give the hint in most effective manner as much as we can. And so the first revision of it, we had some feedback from them. We made some modification things. We used to have regular, we started with a face-to-face with Microsoft, explaining them why we are designing this, got their feedback. And then every week we used to meet with them with results from either our simulation or real silicon and show them that, hey, we may need to adjust something here and things. And they have been great partners in all of this.
So you guys had a face-to-face with Microsoft and weekly syncs, and it has been like this evolution process throughout the couple of years. So how's it come along? I know we've already covered some of this, but what are like some of the benefits of Thread Director?
Yeah, so as I was saying, right, in terms of, so every generation, since our core, P-core and E-core microarchitecture evolves, our performance deltas change, right? So when we started with Alder Lake, VNNI was something that we had higher performance delta. Ever since Meteor Lake and Lunar Lake, that has gone down. But we kind of help and address and figure out that where we expect performance delta, we want to guide operating system to use right cores, right? So instructions is one part of it. Another one becomes power budget, right? If let's say that now, with AI PC and everything, NPU and GPU are becoming quite critical because, Copilot is using NPU quite a bit. We have creator software and, other segments that are using GPU for their processing and things. And we want people to use them because we are creating these execution units for, folks to run their new bright ideas on. Right. But if you look at smaller form factor, let's say an OEM designs like a 15-watt 20-watt system, and a lot of power budget goes to all these different IPs other than CPU, and lesser is left for CPU. Well, in some cases, E-core actually might turn out to be more performant, right? We have seen cases like that. So thread director is a way for us to communicate to operating system that, hey, the P-cores are no longer most performant because you are running in constrained environment. E-cores are now more performant, so use them for your performance-aware scheduling, right? So those kind of the things that, that's why we build this interface to hint to operating system, because if you kind of think about it, SoC has intrinsic knowledge about some of our constraints, where we have benefit, how it works from one generation to another generation, etc. Right? That's all built inside SoC. While operating system has their own knowledge. What's the priority of the thread? What's the QoS of the thread? Right? Is it foreground, background, or something?
Right.
What's the thread runtime? Is it dependent on some other work? That's a lot of software knowledge inbuilt. And instead of overloading operating system by saying that, oh, every SoC you handle things differently, this interface allows it to us to give OS a hint, and then OS can consume it with other information to come up with ultimate decision.
This is great because it makes it makes it a lot easier. Well, quote unquote, a lot easier for OSs to figure out what's going on. That way, they don't have to have a dedicated one for each type of SoC. So that way, it just does that. And it also shows out that something that's pretty cool is the evolution. Like we can see how Alder Lake and Raptor Lake had some. That was kind of the first iteration of Threat Director, and then we went to Meteor Lake and how it completely changed by the addition of a low power island. So can you tell us how was that evolution, right? Because you went from P cores, E cores, and now you have a completely new set of cores and a whole new set of, I guess, responsibilities.
Absolutely. So let's take a step back and kind of understand the motivation for the low power island, right? The low power E-cores that we had. We knew in Alder Lake and Raptor Lake, the hybrid that we are introducing is performance hybrid, because we wanted to kind of get into desktops, be the top of the line on performance, like, give the maximum possible for our emerging use cases, etc. Now, at that time, we also started to think about how do we use it for efficiency purposes, right? One of the things that we see, and if you look at the analysis of power KPIs and things that we do, Uncore becomes our bigger bottleneck when it comes to power, right? So one of the natural things was, can we separate out some cores that have their own island and don't sit on the same ring, where the cost of using that ring is higher in terms of power. So that's how we created this low power island, right? Meteor Lake was our first step towards it. Yeah. So if you remember, on Meteor Lake, we had two low power E-cores, right? That's also and that was because we wanted to kind of get to the ecosystem and say that, hey, now we have this low power island, let's start enabling them. It had some use cases that could fit on the low power island, and eventually it evolved into Lunar Lake having 4 cores on there. We could fit more stuff on the 4 LP cores that we have, right? But what Meteor Lake helped us do is put one step forward on, because it takes time for software to evolve from usage of just performance hybrid versus using now efficiency and things, right? OS consuming hints that, hey, now I'm doing consolidation on one island. I recommend that use one die or one island more versus the other island for efficiency perspective. So Meteor Lake helped us get through that step. And we learned a lot from there, and then we created Lunar Lake, and now we have Panther Lake, right? So it really kind of is a continuous journey as I see it.
Yeah, it's pretty crazy because we went from, like you said, Alder to Raptor Lake, when we should go in like performance. Therefore, the scheduling and the thread director was kind of planned in one direction. Going to Meteor Lake, Lunar Lake, and Panther Lake, which they're a little bit more focused on mobile laptop and battery and energy efficiency. So you have to okay, we already have kind of work the performance, but we have to redevelop it for now when it comes to more efficient, or there's something else that is more meaningful to the end user.
Yeah, and that, they're also thread director, if you look at it, the interfaces are the same, right? We don't change anything from Alder Lake, Raptor Lake, the interfaces are consistent. But the information it communicates to operating system that, hey, now we have this one die island or die containment because SoC thinks it's better to consolidate work on one die. Those are the things that have evolved on the information that gets passed from SoC to OS side.
Yeah, one of the things that has changed was how the scheduling was done from at the beginning to the cores. So I think we started with just the scheduling will be prioritized P cores, but then later on that changed.
Yeah, so it's an option that operating system provides to customers like OEMs, end users, on how they want to kind of provide that. One is a standard scheduling, where we basically say that start from the P core, and we use standard scheduling for Alder Lake, Raptor Lake very heavily, right? And kind of because from efficiency perspective also, because you are putting E-cores on the same ring, it worked out better that maybe get the job done faster and get that ring into lower power state. Right. But when we moved to Meteor and Lunar, we had this island separated out. It was kind of higher in terms of efficiency capabilities. So with Microsoft, we used an approach called as hetero scheduling. They had this approach introduced in Lakefield also, right? We used this approach called as hetero scheduling along with thread director hints to find out that, oh, it makes sense to keep work on low power island. Oh, by the way, now because concurrency exceeded, or we are going really high frequencies on low power island, you should probably migrate the work to compute island, etc. All of that hint come from hardware, right, as part of thread director. But we use this hetero scheduling in certain configurations, such as when running unplugged on DC power, right? Because we wanted, the intent there was that when I'm unplugged, I'm on airplane. Yes, I care about performance, and our E-cores are performant enough. I mean, they're very capable cores, but I also care about efficiency at that time, right? I want it to last for my 5-hour plane ride if I'm going from coast to coast.
Right.
So that's where kind of the hetero scheduling came into picture, along with the feedback from hardware to kind of keep the work on LP cores, or if it exceeded capacity, go to the next complex that we have.
So throughout the different generations, we have there's some changes, or there's some like different options that people can have, or partners, or we can have when it comes to scheduling P cores or E cores. Can you tell us a little bit more how that works?
Yeah, so let's start from Alder Lake and Raptor Lake, right? We wanted to kind of maximize performance there, so we always started with what we referred earlier to standard scheduling. And even from efficiency perspective, because you are putting the E cores on the same ring, which is a performance ring, right? It made sense to start with P cores for efficiency perspective also, so you can get work done faster and go into idle state, right? Now, as we kind of evolved into low power island, Meteor Lake, Arrow Lake, Lunar Lake, Meteor Lake and Arrow Lake were really our start to that. We kind of started to give options to our customers, where thread director would provide feedback to operating system that these are most efficient cores to start from. And then there is an option to use hetero scheduling that we discussed earlier, where OEM can choose through a PPM package and say that I want hetero scheduling for when I'm unplugged, I want to maximize efficiency, right? And start from there. So on Meteor Lake and Arrow Lake, we kind of had 2 LP cores on our low power island. So we started from those. We learned a lot from that in terms of what is needed for software enablement, what kind of hints are needed, any changes to hints that get sent from hardware to operating system, such as, hey, now it's better to consolidate work on this low power island versus expanding it to the compute island, etc. All of that was kind of a starting point for a Meteor Lake and Arrow Lake, right? And then as we moved to Lunar Lake, where we had 4 cores on low power island, we were able to put more kind of emphasis on keeping work there. And remember that our E-cores are very performant, right? So it's not like they are just there for efficiency. They can give decent performance also in terms of, making sure that we are getting performance benefits out of it. So for day-to-day tasks like office productivity and things, we get great performance out of it, as well as efficiency as well. So that's where kind of the evolution coming from using more energy-aware scheduling in terms of starting with LP cores first, and then moving on to compute complex to use P and E cores on the compute complex came about.
Yeah, that's pretty cool, pretty interesting to see how, you have so many options. And one thing that I actually just learned, and I think it's pretty cool, that when it comes to, there's also a difference of how on the behavior when it goes between DC or AC. Like if it's if it's on battery, it's one way. If it's directly to the wall, it's completely different way.
And thanks to our partners like Microsoft, who has helped build this flexibility or to offer to customers, where we can give hints to Microsoft and they can offer this flexibility, right? Because our hints come through thread director, which one are performance efficient cores. They offer the flexibility via PPM to our customers, and the whole ecosystem kind of works well together to bring this to market.
One of the features that is pretty interesting to me when it comes to Lunar Lake is we have developed these containment zones, OS containment zones. Can you tell us a little bit more about that?
Yeah, and this was again with Microsoft, especially on client OS, since they are predominant vendors there. What Microsoft had done was we provide them the thread director table that talks about which ones are the efficiency cores, low power island cores, and which ones are the compute island cores, etc. Right? So they took this information and they created something called as zones. And so the LP cores was efficiency zone, the compute cores were a hybrid zone, and in Lunar Lake that only included P cores because we didn't have any E cores on the compute zone. Right. But as we know on Panther Lake, it's different. So whatever sits on the compute zone are part of hybrid zones, right? And then if all cores are used, that's called none zone because you're essentially not using any zones. So what they do is when we use scheduling like heteroscheduling, we start from the efficiency zone. If we are able to keep all the work contained there, the work gets executed there, like a Teams 3x3 call. We have shown it in Lunar Lake also. Most of the work gets contained there. Our compute complex is essentially idle that time. But if you start like compilation or some productivity along with Teams call, we want to make sure we have our P cores to, or compute complex P and E cores to use them. Right? So then if hardware provides feedback that, hey, these cores are not efficient anymore, then OS moves the work to the hybrid zone, right? And based on their own thresholds and things also. And then if you run something like Cinebench MT, which needs all cores, it goes to none zone, right? So it's a pretty cool thing that Microsoft kind of developed based off of feedback that we kind of provide. They kind of use our first initial HGS Plus or thread director feedback to create these zones and then dynamically adjust between them to maximize efficiency.
No, that's pretty good. Is that tied directly? I know we had a lot of feedback from our customers saying like they also wanted to have to some degree, by customer means like the LHP and other ODMs, they wanted to have some degree of control or determine how to dictate how the thread director will work or how the threads will land.
Yeah, that's a great question about some of the power management enhancements we have done in Lunar Lake, right? So one of the asks frequently we got from customers was, hey, how do I, like, let's say I'm in cool and quiet mode, okay, my user selected that, or my system, I see it's overheating too much, I want to go in cooler because I don't want the fan to ramp up all the time and things. How do I communicate that I did this at a platform level to you guys in SOC, right? So we built an infrastructure to communicate the system intent to hardware. And in Lunar Lake kind of time frame, we had our platform software DTT, which most of the OEM use, communicate that to us. And then we did some power management actions, resource management, frequency being one of the resource based off of the input that we get from them. Right? They really like this feature because it helped them get performance when they want, because just because somebody is running unplugged, that doesn't mean that they don't want any performance. They have some performance expectations, right? If I'm double clicking on a file, I want it to open within 500 milliseconds or something, otherwise I treat it as a user experience issue. And my bar on that is probably quite low. Some people can recognize 100 milliseconds, I don't know. So, but they want some decent, reasonable user experience along with maximizing efficiency. So they started to communicate that hint to us. We use that hint internally to drive some of the power management decisions. It's not directly related to thread director in terms of shut down some cores or anything, but it's for our internal power management. And that hint is absolutely invaluable, and you will see we are doing more and more with that.
Yeah, I think our customers will value a lot that feature because, I mean, depending on what type of system or laptop they're doing, they can actually adjust that, like if you're doing like a thin and light or a gaming or depending what you're looking for.
Absolutely, yeah.
So throughout the evolution of Thread Director, what has been one of the kind of the biggest challenges you guys had to overcome?
Yeah, that's a great question. So, I mean, if you kind of think about it, combining two microarchitectures on one SoC was not a small thing, right? Our architecture and SoC team pulled off a big victory with that. But getting it to work in terms of, guiding software to do right things, like how do you handle affinities? Yep. Because I don't want to, so we had to work with the ecosystem to say that, hey, we don't recommend using affinities because you're actually going to then not get maximum performance if that's your intent, if other IPs are taking power budget, right? when Threat Director first came into effect, before we got hardware, we wanted to iron out as many issues as possible with our operating system vendors. So we created emulation platforms. Our Israel teams kind of worked hard on it to get the emulation platforms out so we could run actual workloads and say that, oh yeah, this is where I need the interface adjustment, or this is where I need the OS adjustment and things, right? We also had to build a very flexible interface because this was the first time we were introducing this. So let's say we find out something later, when we get the first silicon. We didn't want to have too much dependency on, oh, now I can't do anything about it because it needs a big hardware change and I don't have a room for that, right? So firmware kind of had to be creative about it and provide us flexibility with that. So there were a lot of exciting times in terms of, early meetings with our Israel partners, Oregon partners to make sure that we get everything going correctly.
Yeah, it's a pretty huge effort to get, now that you describe it to us, because you're completely right. It never occurred to me you have to create emulators to make sure that things are working correctly, because the last thing that you want is having silicon back and all of a sudden, I don't know, I forgot to set a flag or some research or something. It's okay, it's dead on arrival. But yeah, it's pretty impressive.
Yeah, I mean, the emulation part in my mind kind of did a lot of heavy lifting to get us ready when the silicon arrived, right? So, which I think was a pretty cool thing. So.
No, that's great. So I guess the next question is probably tied to this. To your answer is, what are you most proud of when it comes to the creation of and the evolution of Threat Director?
Oh yeah, I mean, just the massive amount of kind of collaboration across organization that happened. I mean, you're talking to me right now on this topic kind of as one representative of it, but there's a whole army that is behind it, right? We have our operating system teams that work with Microsoft from Microsoft Technology Center, MTC. We have our architecture team, we have our, firmware and SOC teams. Everybody coming together and pulling this, right? And then we also have that, how do we want to manage our ISV partner communication? What do we want to tell our OEM partners, right? With respect to ISVs, if somebody is having something like affinities, hey, let's go work with them. So when Alder Lake was being created, we tracked every software release milestones and things very closely, like libraries, compilers, operating systems, everything, to make sure that everybody has to be kind of dancing synchronously, right? If one misstep, and then we would have fallouts on other things. So that's something that I'm really proud of the whole team did. Again, it's not just me, it's the whole village behind it. And that was a really rewarding experience in my mind.
I think I really like where we are now in Panther Lake. We've taken the cores that we have, we've optimized them, we've polished them, we've gotten them into a good system, we've got the right amount of compute for the product. So I think that's great. But I'm really excited about the future as well, right? We're hitting our stride in how we're executing and what we can deliver to the end users from a CPU perspective. As the E's in P cores get closer together in their commonalities, this is good for Intel as well. And so I'm really excited. I guess in terms of accomplishments, I love my Lunar Lake laptop. I'm going to look forward to my Panther Lake laptop. Right, but those next gens, I'm really excited about.
For Panther Lake, without spilling the secret recipe, what is the thing that you are looking forward to for it?
Yeah, that's a great question. First of all, I'm waiting to get a Panther Lake laptop for my day-to-day use, really, because it's going to be amazing.
Yeah.
We have process, we have improved P and E cores. Stephen is going to talk all about it during tech tour and everything, right? You'll learn more on things. We have even enhanced power management features that I'm really excited about, which kind of balances performance and power, user experience, focusing on what really matters to the user. And bunch of things coming out. So I'm quite excited and to get my hands on a laptop that I can use every day.
So as I mentioned, I love my Lunar Lake laptop.
Right.
So Panther Lake is going to take that Lunar Lake laptop with a great battery life, and you're going to have that same battery life experience. But it's also going to have more performance. It's going to have more throughput. It's going to have more capabilities, so it can run more complicated workloads. And so it's going to be that great battery life laptop with a punch of performance.
Performance hybrid architecture allowed us to deliver performance to the users when they needed it, but much of the work we do, either in enterprises or at home, are background tasks that don't require performance. And so we're able to move those to a much more efficient architecture, and then the user sees long battery life and good performance. It's an and, not an or.